Hi, Yin Yo. Good. Some of you guys have already logged into the Meet, Google Meet, and try to test. This is good. So Yin Yo, do you want to try the audio and the camera? Just to make sure that it's working. All right. I guess that's Yin Yo. Yeah, good. Camera's working, but I did not hear you though. Ah, very good.
Okay, I just opened my mic.
Okay, good.
Can you hear me?
Yes,
Thank you.
working very well. All right. So Yin Yo is all set. Okay, hi, Wei Yo and Liang Yu, Lawrence, Bing Rui. yeah, the elbow touch, or yeah. And yeah, Yin Yo, I just saw you on Google Meet, and Bosch, 博智. Hi, you all. Yeah, Wei Yo. So if you guys want to try Google Meet, okay, I see Wei Yo. Maybe you want to talk and see if the audio is working. Just say hi, maybe. Hi, but that's text-based. Okay, it's okay.
Polly,
Hi.
does it work?
It does. It does. Okay, so I guess
Okay, thank
that's
you.
博智's camera also working. Wei Yo, your camera is working fine. All right, good. You guys may leave.
Okay, thank you.
Lawrence, I guess you are Lawrence. 熟人, could you turn the camera on? Great, working fine. Do you want to try the audio in case you want to just talk, asking questions during the exam? If you don't mind just typing things up, it's okay. It's not necessary to test the audio. Okay, I guess you would probably prefer typing. Oh, I'm in the library. Okay, of course. Shh. All right. So if you're taking the exams in the library, that's nice because the background is going to be quiet. So you can still ask questions by typing. Okay. So that's it. So Lawrence, you're fine. You may leave Google Meet as well. Hi, Tim. Yo, Ting. Would you like to turn on the camera? Okay. Yeah, the resolution is a little bit low, but it's okay. Are you gonna take the exam in the library? Yo, Ting. Probably. It looks like it's a library because I see books and magazines. Maybe. Okay. Yeah, good. I think, as I mentioned, library might be a good place. It's just that you cannot talk, but you can still type, right, on the chat in case you have questions. Just so that you can hear me, because some students might ask, and so you can hear the audio. All right, good. You're good, Yo Ting. Should we enter the Google Meet? Liang Yu, yeah, definitely try the camera out and see if it's working for you. So you don't have to adjust tomorrow in a rush. Bing Rui, all right. Yeah, try turning the camera on. Okay, Bing Rui. Could you like lower the camera angle a little bit so that I can see? Okay, that's good. Okay, and Bing Rui, would you like to test the audio or you don't mind just typing questions up? And Liang Yu, let me let you in. Okay, Liang Yu, you're good. Okay, your camera is obviously good.
Hear me?
Yeah, Liang Yu, I can hear you also.
Okay, thanks.
Okay, you're good. All right, Bing Rui, I think you're good. Your mic is not working for me. Say something. Qian, would you like to? Your camera is good, Qian. Would you like to say something and test?
Hello.
Okay, great.
Is it okay?
Working fine. Yeah, it's
Okay.
working perfectly.
Thank
So
you.
once you finish testing, you may leave. And the next one is Sean. All right, your camera is good, very clear. Okay, this is a nice camera. But the network doesn't seem to be working very well. But it seems to be okay. Would you like to try if you want to speak maybe during the exam?
Hello, hello.
Works very good. So very well. So Sean, you're also good. You may
Thank you.
leave the room. Good. Many of you have already tested it. Okay, and this is Yuhao. Okay, Yuhao, would you like to turn on the camera and try it out and see what camera angle you need to... Oh, nice. Okay, you use a virtual background. Good. But during the exam, you need to take the mask off so that I can see you. Okay, good. And those who did not test mic, then if you have questions, you need to type it up. Okay, I hope it's okay. Good, so then Yuhao, you're good to go. Okay, just 3 more minutes. 4 more minutes until we start the next lecture. Okay, that's a very good question. So when I call to check your ID, I need to see the face. But once after that, you can wear the mask back on. Yes, Liangyu, there will be a Google form link for the exam tomorrow. And those links, the Google Meet link, will not be the same as the one we're using today. So the new Google Meet link and the Google form link would all be on the exam 1 channel. So they will be up there tomorrow, very early morning. Good. That's a very good question. Yeah. Because we need to be considerate, right? Because there's a regulation about wearing masks in public area. Yeah, Liangyu also, thank you for bringing the question up. Those links, very important links, one Google Meet link and the Google Form link. Both of these links will be available from the Exam 1 channel. Is it okay to reconnect to the Google form if the network is not that stable? I'm not so sure about the dorm. Yeah, okay. So usually the dorm internet is reliable, but I understand that the dorm internet has been managed by students. And it seems that over the generations, the quality of management gets ever slightly worse every year. So you see, Liangyu, that's a very good question. That is also why that I mentioned in Exam 1 channel that you want to submit the form. Okay, once you fill in the basic information, that way you get from email the link to the form, so you can come back to work on the form again. I understand. Yeah, Liangyu, that's a very good question. Yeah, so in exam 1, you should see me saying that once you fill in the basic information, submit at least once, because you can always resubmit to override. So submit once. That way you get the link from Google, okay, immediately, okay, after submit. So if the internet is not good, you can always go to the email and click on the link and come back to the form to work on it. Very good. And you know what? Let's start the lecture today. So the to-dos are actually quite straightforward because we do have a major exam coming. So for this week, you have only quiz 13 due on Saturday. Okay, so the assignment load is the lightest, but we do have exam coming tomorrow. So make sure you go to the exam 1 channel here and read through all the bullets. Okay, so I think starting from the first post from Polly, okay, the time, the date, okay, the Google form, get familiar with using Google form, okay, and you need to also tune into a Google Meet session, so Polly can check your ID, because this is regulated by the university. We need to confirm the identity of the student taking the exam. And the exam is going to be super long. It's designed to be longer than the time it requires. Okay, so even though that I assigned 100 points for the exam, so you have 100 points to earn, but you only have 90 minutes to work on it. Okay, so if you can look at the points allocation and go through all the problem first and start from the one you find the cost price ratio is the highest. Okay, so the problems that you think you will be able to earn the points with less amount of time, because that will earn you extra time for the problems that might be taking more time. Okay, and so I'm not gonna go through the detail again. Guys, definitely read it through in detail, and in case there's any questions still, ask. All right, now let's go to the first topic today. We are not yet done with DNS. In fact, there's a major part of DNS we are yet to talk about, because DNS is what to provide mapping to IP address lookup. We have not yet talked about exactly what these mapping, hostname to IP address mapping, sorry. Did I say mapping to IP address? I meant hostname to IP address mapping. And DNS is to provide lookup of these mappings. So we need to talk about today. What are these mappings? How many different types? And how we're storing them? And how some of these DNS servers might be caching some of the entries they get from the other DNS servers. So here's the video.
DNS servers also cache data. And this is not the first time we hear this term, caching. The first time is when we were talking about web caches, isn't it? So web cache there stores web objects, so we could reduce delay. We could save some network bandwidth. You see here, DNS, for the same purpose, also caches IP name mappings. Okay? The goal is also to reduce delay to save network bandwidth. So you see, caching is actually a very general technique for data transferring services to try to avoid repeated download. So let's go on to DNS caching. So each of these mapping will be stored at the name servers once they acquire them the first time. So these entries will be there on the server's disk for some time. So the interval is called the TTL. What it stands is time to live. So during this time, the entries stay. Once the time expires, the entry is timed out, removed, okay, from the entire disk. So, an example, a local name server might store the mapping for a top-level domain server so that the local name server doesn't need to go to the root name servers a lot, okay? Again, trying to conserve the root server's capacity, right? And the cache entries may go outdated. This is happening when the entry is not yet timed out, but the host there is already changing the IP host mapping at the authoritative DNS server. In that case, the clients worldwide will continue to get the old mapping, the out-of-date mapping, until 2 days later. This is usually the TTL of DNS mappings are set to by default. So 2 days later, the clients get the new mapping. So that's why we don't change the hostname IP mappings all that often, because during these 2 days, your customers will have trouble reaching you. So DNS caching, this is another protocol. It's defined in this RFC 2136. And by the way, the body, the community defined all these internet protocols. Okay, writing all these RFCs is called the IETF, the Internet Engineer Task Force. Let's take a closer look at the entries that DNS servers are storing there. They're called the records. Well, to be more precise, the resource records, okay? And each look like this, a tuple of 4 elements. This is usually the host name, and this is the IP address. And this is TTL, the time these entries should stay on the server. What we haven't talked about is this type. There are actually 4 of them, not many. Let's look at them each a little bit closer. So first is type A. It's the most classical one, which says hostname at the name and IP address at the value. Essentially, this is the query, and this is the answer. Querying for this host, answer is this IP address. Second type, let's go here. The C name type. What C stands for is the canonical name. So what this does is corresponding to the second service we mentioned way earlier when we started talking about DNS. So it's doing what? Alias, the name alias service. So what it does is here, the entry there, name is the alias, the Q short one, and the value is the actual name, the canonical name, the real name. So here we have .ibm.com, cute and short, easy to memorize. But the actual name for that machine should be this, server is backup2.ibm.com, right? So value is the canonical name. Third, let's look at this type, the MX type. So this is mail service type, and this corresponds to the third service that DNS provides. Name is a domain. Value is the mail server for that domain. So name here could be gmail.com. And the value will be what? smtp.gmail.com. Straightforward. Last type we have not yet talked about. It's actually not quite the fourth service that we mentioned about DNS providing. It's actually called the authoritative name service entry. Right? So the name there is a domain. Okay? But it's not the top level domain. It's usually the second level domain. The value is the host name of the authoritative name server for that second level domain. So this is for the TLD servers to store all the authoritative name servers for all these subdomains. Right? So NS type entries are mostly in the TLD servers. Next, the DNS Protocols Messages. So the servers exchange just the query and the reply messages to each other. They are in the same format, which is exactly what I'm showing here. There are 2 parts though. From here and up, this is the message header. From here and down, the data part, where the actual mapping, actual entries are being carried. Now let's focus on the header a bit more. The first field is called the ID. It's 16 bits long. It is used to identify a pair of query and reply. Right? Next thing, the flags, then you identify whether this is a query or this is a reply. So this is how server know that, okay, this reply is for a query that carries the same ID. In the flags, you might also see a certain client is saying that, can I do recursive query? In the flags, you might also see certain DNS servers saying, no, let's disable a recursive query. And coming from the authoritative DNS server, you might see this flag being turned on. The reply is authoritative. There are 4 other fields in the header, these. So these are specifying the number of questions, number of answers, number of authoritative replies, number of additional informations. Now these are to serve the purpose down here in the data part, because the number of questions a DNS message can carry is variable. Now in order for the receiver to know how many lines, how many records it reads, it looks up here to find out, and reads up to this point and then to the next part. So that you will not be confusing a regular reply with an authoritative reply. Right? And next, let's focus a little bit more in the data part. Okay, so in the question fields, you will only see this, the name and type in a query. That's all. There's no value, there's no TTL. In the in the answer entries, however, then you see the full RR, full resource records. Authority here carries records for the authoritative DNS servers. If you have also the full RRs, it's just that those RRs are the authoritative server RRs. Last is just additional information. I see rarely this part of the data being used. Now let's try to put our knowledge into use. So here the scenario is you need to set up your network for a startup, network utopia. All right, so 2 things you need to do. First, register your domain name with the DNS registrar. Now being a .com, you talk to this company, Network Solution, who maintains the .com TLD server. Right? Second, you provide also the name and IP address mapping of the authoritative DNS server you'll be setting up. Okay, so there could be a couple of them just in case the first one failed, there's a backup. At this point, the registrar there, the network solution there, will try to insert 2 records. Okay. One is, of course, the name and IP address mapping. Second is the domain name and the host name of the authoritative server. So you see here, name to IP address is the type A, the classical one. This one here is the NS type, the authoritative type, where the TLD stores domain name and the authoritative DNS server mapping. Good. Now back home, you need to set up a couple of these authoritative servers for sure. But inside these authoritative servers, what do you store? Well, if you want a web service, you need type A entry that keeps the name of the web server and the IP address of the web server. If you wish to have email service, then you need to set up an MX entry maintaining the mapping from the mail domain to the mail server's host name. And maybe the IP address of the mail server entry, that's another A record in the authoritative server. All right, so that's how you get your customer to see the IP address and therefore being able to visit your website. Attacking DNS, this is the last bit of DNS. So we're going to talk about attacks in 3 parts. First is attacks targeting the hierarchy of the DNS. Second is to target more the client who need DNS service. Third then is to exploit the DNS service to try to pull off attack for some other targets. So let's go back to attacking the hierarchy. So a hacker could actually hack down a number of machines around the internet and have these machines bombard the root servers with lots of DNS queries. Right? So having very few root servers around, this can potentially be dangerous and bring down the DNS service entirely. But nowadays, now it's hard to pull off, mostly because the local DNS servers will cache the TLD servers. This allows all the local servers to bypass the root server entirely. Right? So there's not much traffic going to the root. If the zombie machine sends a lot of queries, chances high that they'll only go to TLD instead of the root. Right? Not to mention that one could set up firewalls nearby the root servers. So those very few root servers are well protected in a way. Now, attacking the TLD servers then is more feasible, all right? Because queries then all go to the TLD these days. Good, so it's more dangerous. But the thing with the TLD server is that the number of these is way higher than the number of root servers. So the hierarchy there is pretty robust, to be frank. The second type is the redirect attacks, but I would rather call that this is attacking the user of the DNS service. First is the man-in-the-middle attack. What the hacker does here is just to intercept the queries. Therefore, it's not going to reach anyone in the hierarchy, and therefore no answers back to the users. Second one, on the other hand, I think is meaner, DNS poisoning. So the hacker there is actually sending false replies. So when local DNS server caches these replies, the users will be thinking, "Ooh, I thought I'm going to the www.google.com, but it's actually going to a hacker's website." Not very good. So nowadays, network admin for the local DNS servers needs to be careful and check the sources of these replies. Last one, exploiting DNS for DDoS. We actually hear about this already. So this is in chapter 1, I believe. Okay. So people are sending queries. Hackers can spoof these queries and replace the source address, with the IP address of the attack target. As a result, the servers in the hierarchy will be all sending replies to this guy here, and therefore denying this machine here to go out and reach the rest of the internet. But this is also a bit hard to do because you have to hijack enough of these queries. You need to spoof enough of these queries, right? So you need amplification in order to make sure that the service is really denied, at the target IP. And that's all for DNS.
All right, so that was DNS. And by the way, the source address spoofing attack happened just 2 weeks ago. Remember that we talked about Facebook was not working. That's because the DNS announcements they have are withdrawn by the hackers. So the hackers pretended to be Facebook and asked the DNS servers to remove the entries for Facebook. So that was DNS. And let's move on to this new topic. It's also in the application layer, but it's working a very different fashion, right? Previously, what we heard about, email, HTTP, DNS, FTP, all these internet services we see today and the application layer protocols we see are client-server based. This other model, P2p, we have not yet seen any example. So the video's coming up. First, let me introduce P2p and why P2p. How can P2p based application be better than the client server based? And then I'll introduce an example called Bittorrent. That is the number 3 topic here, BT. So overview, this takes about 10 minutes.
P2p applications. To be honest, this is one of my favorite sections in chapter 2. All right, so P2p architecture. as opposed to the very simplistic client-server architecture where we have always-on service, in P2P, there's no more always-on servers. Instead, we just have these arbitrary peers directly connecting to each other, communicating to each other. As you see, hey, these peers are very likely mobile end systems. So the connectivity there is intermittent, meaning loosely connected, on and off, on and off. And the IP addresses to establish physical connectivity can also change over time. So it's actually hard to maintain a fully connected session as a user moving around, for example, on NTU campus. So we'll talk about two applications. One is for file distribution. The other is for voice service, voice over internet service. So the application for file distribution is Bittorrent, and the other one is called the Skype, an internet telephone service. We're not going to talk about applications in video streaming, but there are actually quite a number of these video streaming systems in the early years that works in this peer-to-peer way. So for example, this one, Kankan from China, that's Mandarin Chinese, meaning take a look. It was a very well-established service. Okay, before we talk about all these P2P application examples, let's talk a little bit more about the benefit of shifting from the client-server paradigm to the P2P paradigm. Right, there must be a reason why people choosing to do P2P instead of client-server. And we're going to use an example, very simple, to transmit or to distribute a file from one server to end users. Each of these users will be limited in terms of the uplink as well as downlink capacity. So look over here. This is peer I. Okay, so its uplink capacity is called UI, and downlink capacity DI. Okay, so the same fashion you see therefore for user 1, uplink bandwidth being U1, downlink bandwidth being D1, and same for user 2 and user N. The server is over here. The uplink capacity is US. Well, therefore, the downlink capacity is DS, although that we're probably not needing it in the calculation. All right, so file, one big file, size being big F. So this is the setting. Now let's calculate the time it takes to distribute the file to all end users. First, assuming client-server model, meaning server here will need to upload the copy and distribute it to each of the clients. If the uplink capacity is US, therefore the time to send one copy will be F over US, and to send N copies altogether, NF over US. And this is the term that we have here, because the overall file distribution time will be limited by the uplink capacity and the minimum client capacity. So this is the case where the server is the bottleneck, and this is the case where a client with the minimum downlink bandwidth is the bottleneck. Now, the client carrying the minimum download rate, let's assume the value is D mean. Therefore, the download time is F over D mean. The smaller the D mean is, the longer the download time is. And therefore, you see, again, in case the server is the bottleneck, the overall distribution time will be bounded by this guy. If the client is the bottleneck, the overall distribution time will be bounded by the F over D. Now, that's considered an N that's increasing over time. Right? Talk about the scalability of the system. The file distribution time, how does it scale with N increasing? Well, this term suggests the overall distribution time will increase linearly in N, okay? While the minimum bandwidth for downlink might not change all that much. Okay, so potentially the overall delay, if we change N, is growing like this. Now, the same, calculating the time for file distribution, but this time in the P2P model. Meaning, hey, this is one of the peers, and each one of these users is also one of the peers. So they could be downloading a copy from the server, but they could also be uploading a copy for another peer. Now, the server transmission time, this part now, the optimum is just to send one copy uplink. So F over US. Client there, in case it's the bottleneck, it's going to be bounded by F over D min, which we explained. And clients overall as aggregated system, okay, must download NF bits, okay, and the maximum upload rate is the sum of all the uplinks for all the users plus the uplink capacity of the server. All right. So in a way, the file distribution time here for a P2P system, it's bounded by either bottleneck at the server, bottleneck at the client, or bottleneck as the system as the whole. If you want to download NF bits over this much bandwidth entirely, right? So we have the server being the bottleneck case, one of the clients being the bottleneck case, and the system overall being the bottleneck case. So NF bits that needs to be passed out, okay, over the entire capacity, entire uplink capacity of the system. So the distribution time bounded by one of these two terms. All right, now consider again if n is increasing over time, right? The scalability of the P2P modeled file distribution system. Which of the term you think is going to grow with the n? Yep, this one over here. Right? It also grows linearly with the n. But if you look closer, when the number of users also increase, this term also increases. Yeah. So does this. And each peer brings service capacity. If you recall, this is also what was talked about called the self-scalability, a nice property of P2P architecture. Okay? As a peer join, right, the peer demands service, but the peer also contributes its own uplink capacity, okay, to help others to download. Okay, so this grows linearly with n, but this also increases, but not quite sure if it's growing linearly. But overall, it's going to be better than what? The linear growth. So the growth is probably more like this. Let me use a very simple scenario to contrast quantitatively the differences between client-server mode and P2P mode in terms of the distribution time. Right? So scenario goes as this. The client's upload rate is small u. And if we want to upload the file over this client link, F over U, and let's say that that's 1 hour. And the server uplink rate is 10U, 10 times higher than the client's uplink rate. And let's assume the downlink capacity of all the clients are just so large, much higher than the server uplink rate. Right? So bottleneck is actually here, the user uplink. Right? Now, think. Let's assume that there are 10 users. Okay? In client-server mode, what is the distribution time? So let's see. 10 users, 10 copy of the file, and the uplink capacity of the server is 10U. Therefore, what? F over U. And this is 1 hour. So in this case, yeah, the distribution time is 1 hour. Clear? Now, in P2P mode, let's see. We have what? 10 files, 10 copies of the files that needs to be downloaded overall, right? And what is the total uplink capacity of the system? So user has 10U. Each client has what? 1U. So 10 of them, also 10U. Altogether, 20U. And how much is this? Half of F over U, and this is what? Half an hour. And is that right? it is right? In P2P's case, 10 users, only half an hour. Okay, so you see the growing trend, linear in client-server mode, but sublinear in P2P mode. And this illustrates this characteristic of P2P system very well, self-scalability. Right? And this is the big advantage of running an internet service in the P2P architecture over the client-server architecture.
Okay, how do you like P2P? Okay, so let me know on the chat whether you prefer still client-server. Okay, but tell me also if you prefer P2P. Next is an application that's based on P2P. And this is very similar to FTP, file upload, file download. It's called Bittorrent.
First example is Bittorrent. The way the file is distributed in Bittorrent is instead of sending one big file at a time, it's divided into smaller chunks, 256 kilobytes per chunk. And the peers in a torrent actually sends and receives these file chunks. So here's to illustrate the P2P network. Okay? And each of these is a peer. Okay? And the group of peers form a torrent. Okay? And they exchange chunks of a file. Okay? So BitTorrent. Okay. Now, there's one more entity. It's called tracker. So this machine here is actually to bootstrap the process of having a new user joining or a new peer joining the torrent. So when Alice arrives, for example, what the system does is to first contact the tracker and then tracker in return, giving Alice a list of the peers. And this is the initial set of peers that Alice will connect to. Now once Alice is connected to the torrent, then Alice can try to explore other peers and then re-establish connections to these other peers. So, tracker here is to bootstrap the initial joining process. Furthermore, about the operation of BitTorrent. A peer joining the torrent, you've heard it earlier, right? Contacting the tracker to get the initial set of peers. And those peers that are connected to Alice will be Alice's neighbor. And Alice at the beginning has no chunks, but over time, Alice will accumulate these chunks and eventually growing into a complete file. Now, the general operation is this. Each peer will be downloading the chunks while they are also uploading the chunks to other peers. And the peer and peers exchanging chunks, the pair could change from time to time. So they may change the peers with whom they exchange chunks. And the peers might just go away and come back in the middle of exchange. That could be a bit disturbing. There's a special term for it called a churn. Hopefully there's less amount of these churns, but sometimes it's not really controllable. And at the end, once the peer has the entire file, for a selfish peer, he or she might just leave the P2P network entirely. For those who are more considerate, they might remain on the torrent. The part that Polly finds the most interesting about BitTorrent is this. The strategy to request chunks and the strategy to send chunks. Let's talk more about the requesting strategy first. The setting is this. Given a file that many of the peers are looking for, so they'll be downloading chunks for the file. At any given point in time, because they're doing the downloading independently and they might be connecting to different neighbors, they might not know each other, so at any given point in time, different peers might hold a different subset of the chunks belonging to the file. Right? And the way it progresses is each peer then will periodically query the neighboring peers. So asking neighbor 1, neighbor 2, and neighbor 3 for the set of chunks neighbor 1 has for that file, neighbor 2 has for the file, and the set of chunks neighbor 3 has for the file. Okay? So it's kind of an inventory check Now, once the peer receives all these inventory check reports, the peer begins to count which chunk is the rarest in the P2P network. And the peer begins to download from the rarest that he does not quite yet download yet. So that is the requesting strategy. Now, if you think a little bit more about it, why rarest first? If I tell you, look back the previous slide, the issues we might run into are these, right? A peer might come and go, right? So as they move from one subnet to another subnet, it might get disconnected, the IP addresses might get changed. If it's in the middle of the download, those chunks will disappear from the P2P network. Also, right, when some peer finish downloading all the chunks for a file, and if the peer is selfish, they might just leave the network entirely. So in a P2P network, real users will all have this anxiety of not being able to find a specific chunk for a file. And that is also when BitTorrent downloading can go really, really long. It's not because there's not enough capacity, but it's more. Certain chunks are no longer there on the network. Okay, so it's actually quite important this rarest strategy is implemented on a P2P network like this. And another aspect that's interesting is the sending strategy. And I love the name, tit for tat. It sounded kind of fun. Right? The way it works is also very simple. Alice here as an example peer, she will send chunks to others that are sending back to her at the highest rates. Okay? So, hey, if you're generous to me, then I will be generous to you. Okay? Eye for eye, tit for tat. But this simple strategy might create this problem. Other peers are not sending at the highest rate, will be choked then. These guys might not get a chance of downloading certain chunks from Alice at all. Right? This is actually not quite that good. So Alice will reevaluate the top 4 every 10 seconds. So those peers who discover that they're choked, they're not downloading any chunks, they might decide to contribute more uplink capacity. Therefore, as a result, they might get some chunks from Alice back the next round, the next 10 seconds. Okay, so this is the general strategy. Okay, share your uplink bandwidth, then I share mine. But this might not be a good thing either, because some of these peers might be very non-resourceful, meaning they have very, very low uplink capacity. As a result, they might always come up short here in the competition for the highest rate neighbors. So every 30 seconds, Alice will be very generous, okay? And not look at the sending rate coming from the neighbors, but just randomly pick one of them and start sending chunks to them. Right? So optimistically unchoke, okay, a particular peer. Now the newly chosen peer will join the top 4 and receive chunks from Alice. Right? But this is done at the lower frequency, only every 30 seconds. Right? So mostly favoring those who are contributing more bandwidth for uplink purpose, but every now and then, not bias on the uplink capacity of the peers and openly share. Okay? Interesting, isn't it? And let me animate tit for tat here. So Alice here optimistically unchokes Bob. So Bob could be a newcomer into the network. Okay, Alice might randomly discover, okay, there's this guy Bob there. Alice begins to send chunks to Bob. And Bob there says, wow, thank you for all the bandwidth, all the chunks. Okay. And begin to send, also at a high rate, back to Alice. So mutual appreciation at the end. But Alice needs to be optimistic at the beginning, right? Trying to have faith, trust that whoever receiving the data would appreciate the effort. So higher upload rate finds better trading partners. Okay? And so you get files faster this way.
And that takes us to the quiz, the only quiz this week. So this is related to Bittorrent. And you see actually that after I introduced Bittorrent, some of you might feel that, oh, P2P is cool. It's self-scalable. Performance is going to be better. But in the meantime, you see also that it's a little bit hard to manage Bittorrent, isn't it? You need to worry about certain chunks are no longer there for anyone to download. You need to worry about also that in case you don't have much uplink bandwidth, you get choked by other peers all the time and not getting really any data. Okay. So churns is the thing that's causing all these problems. Okay. Peers come and go. But you know what? BitTorrent's trackers also come and go. If you recall, BitTorrent, in order for a random peer coming, wanting to join a torrent, that peer needs to contact a tracker. Okay. So in a way, tracker is the one you go first to in order to find members belonging to the torrent community. So tracker is a very important device there, okay, to allow us to join a P2P network. These BitTorrent trackers can also come and go, so they are not always there either. Okay. So some of the very famous ones are no longer there are these: Supranova.org, Torrent Spy, Loki Torrent, BT Junkie, etc. Okay, so they used to be used a lot as trackers for the BitTorrents, for certain torrents, but they are all gone. The one that remains and still today in certain countries is this guy, Pirate Bay. Okay, this is one of the news, I think, in Sweden. Pirate Bay down. Domain seized by Swedish core, but site likely to pop back up again elsewhere. Okay, so this Pirate Bay has been there as a tracker for a particular torrent for a long time, and that torrent a lot of times serve these peers with copyright protected videos. Okay, and I guess the movie companies, okay, have tried many times to try to take the domain of Pirate Bay down, because Pirate Bay's domain was registered in Sweden. Okay, and finally at some point, I think this is did you guys see the date? I think it's 2006. Swedish court decided to take the domain name down. Okay, but the news, the reporter is saying that well, Pirate Bay might pop back up again elsewhere, but maybe using another domain name. Okay, so you see that the issue is it's easy to kill a tracker because it's just one machine. Okay, unlike the P2P network, you have lots of peers. Okay, so it seems that to bring down a web server or bring down a tracker, because tracker is oftentimes set up as a web server. 2015. Ah, okay, you're right, Yanjun. Good eye. Q1. Why are these high-profile trackers shut down? Yeah, thank you, Chunmao. And Q2, how to make the trackers hard to shut down entirely? Because this is the key question to ask so that you can maintain connecting to the torrent, isn't it? Yeah, exactly. That's Q1, Mindy. Yeah, why? Why do people try to take down Pirate Bay? Try to take down trackers? Chunmao, you're going on the right track. Okay. Yeah, let's go to the Slack. Week 6 quiz 13 is there. Okay. Yeah, so go there. Very good question, by the way, Mindy. So that's Q1 of quiz 13. Why we try to take down, or why people try to take down these trackers. You can probably also guess from the name of the tracker, Pirate Bay. What do pirates do, right? Q2. Well, now this is more playing the role of pirates. How do you prevent the trackers being brought down? Okay. Think about it. guess Q1 is easy. Yeah, okay, that's really good. Yeah, don't worry. This is actually a long question. You don't need to be really fast. Because to answer Q2, it might be a little bit challenging if you want to propose a robust solution, isn't it? Okay. But just, as some inspiration, Team 13 actually say, for Q2, they thought solution 1 is to keep a good relationship with governments around the world. So the courts will not rule to take on some of the domain names. That's one way, but you probably need to bribe many officials. In some countries, it's probably not easy to bribe people. And if you get caught, you might pay even more. So I don't know, solution 1 is really all that viable. And solution 2, let me see, Boris. Making multiple trackers in a BT system. Oh, okay. So if there's just one tracker, it's easy to take down, right? That's build multiple trackers, having multiple domain name. Oh, sorry, Slack kills your iPad. It's okay, you can take time and come back to answer that later. It's due Saturday anyway. 3rd is making part of the BT users to be tracker. Oh, okay. That's interesting. So maybe make the tracker service a P2p service. How about that? But hey, those who are keen to what I just described, P2p services, how do we have the tracker for the trackers, right? If we make tracker as a P2p network, then we need a tracker for the trackers. Otherwise, how do we connect to the tracker P2p network in the first place? Okay, so if you want to design something that's really robust, and resilient, you need a very, very distributed P2P network without tracker. That is not exactly easy to do. But there's a solution called DHT. It's talked very briefly at the end of the textbook in chapter 2.5. It's slightly complicated. We'll not cover it in the lecture. All right. Oh, Liang Yu here posted something. For Q1, Team 2 says it might be so many peers would like to contact the trackers in traffic problems. Okay, that's another reason. Some torrents I know, when a specific video just show up in the market. Okay, for example, the latest the latest Avenger movie showed up, then people probably are all going to the tracker for certain torrent to look for the video, isn't it? So it could generate traffic, and the traffic are all probably directed to a Swedish domain, which means the machines are more likely in Sweden. So the background traffic for residential usage in Sweden might get worse. Okay, that makes sense. And solution for Q2, multiple trackers might be a way to avoid, so use multiple trackers. This is, very typically what people do. In case one tracker is a center of attention, a single point of failure, then you build replicas, and then you can also try to load balance, right, among the multiple trackers. Yes, those are called the mirror trackers. Mirror trackers. Nowadays, if you have ever tried to download freewares, from the internet, you might see also that some of the popular freewares have multiple sites. This is the original site, something.net, And then there are a couple mirror sites in UK, maybe in Australia, maybe. So having mirrors for these trackers. Yeah, so team 2, very good, Liangyu. You are also thinking, right? What's the downside of having multiple trackers? Yes, there is indeed a higher cost maintaining the tracker. But you know what? If you think a little bit more, P2P network is such that we don't need to maintain server. And we have low distribution delay. But now with a cluster of servers, right, the management gets complicated as well. Yeah. But the good side is that usually P2P there, the P2P part inside the torrent, what they're distributing are big files, large files. Okay, so distribution time is very critical. That's lower distribution time using P2P for file transfer. But to look up this initial list of peers in a torrent, that is actually a short message. So it might be okay, right? Using a client-server based model for that to make sure that it's a little bit easier to manage, easier to load balance. So you know what, we did not talk about Skype. In fact, in the 7th edition of the textbook, they removed Skype as an example. Okay, but Skype is done exactly that way. From a new user, go to a directory server to find the list of IP addresses for your friends. Okay, the current IP address of your friends. So later on, when you need to call your friend, you know exactly the IP address of the friend at the time you want to call them. Okay, so the calling part is P2P direct. But looking up of your friend's IP address, which is dynamic, and your friend does not have a hostname IP mapping. No, they are not servers. So Skype needs to maintain the mapping themselves, and that is the directory lookup service. So you see also, nowadays, there are certain services, okay, when the file, the content they're distributing is huge, then they might use this hybrid model, client-server based for directory and then P2P for the content distribution. Good, I see team 1 and team 12. Yeah, so I guess many of you thought that lots of content on the torrent might be illegal. Yeah, that's exactly why these Pirate Bay, all these trackers are being brought down. Okay, these are from the content generators, usually movie companies, graphics design companies, and companies like these. And solution, definitely multiple trackers. Let's see, Bing Ray, team 12. So many trackers around the world and some, okay. Okay, yeah. Yeah. Okay, so we could place some trackers in Russia. Then it's probably harder to bring down, right? Or trackers in Somalia. Okay, the country who really have real pirates, for example. Okay, in the culture, they thought that this is okay. Okay. Well, I mean, hey, trying to think effectively addressing the question. Okay, so morally, it's all wrong. Okay, so, all right, so, and that's enough discussion. Or in China, yeah, 群貌, that might be one way to do it. It is also hard to take down. Yeah, morally questionable also. Is there other applications of P2P? Yes. 加油. Real Pirate Bay, yeah, if it's in Somalia, right? How appropriate. Yes, there is. It's called Bitcoin. It's huge today. It's probably bigger than some of the web services we're using. So P2P is for real and out there. So Bitcoin is built on something called blockchain, and blockchain, if you read about that, is an entirely P2P network. It's super hard to take down. So that's the ultimate P2P system. right. You should not like, admit doing this publicly like this. Okay. Okay, let's not do that. Okay, Polly says so. Okay. Be good. Okay, so the time is up. Guys, feel free to go and move on to the next lecture. If you have further questions, feel free to post. I'm gonna leave the channel here for a little bit so that I can track interactions. A sidetrack on the other hand, today you might find that as Polly is playing video, you hold your question. You actually are more concentrated, more focused to the video, and you pick up the things a little bit better, isn't it? If as you watch video and some of you are typing questions, you get distracted as well. Okay, bye, Yixiang. So maybe in the future, let's try to exercise this more. Let's focus when we are watching video. When it's done, feel free to type up questions. Okay? When the next video is done, Polly will try to come back to the questions. If some of the questions we don't have time to go through during the lecture, Polly will make sure that we address those on Slack. Okay, I'll copy those to ask us anything. You will see the answers there. Okay, so that way we get to see more content more effectively. Okay, bye, Jieming. Okay, bye, guys. Okay, Minhong. Okay, good. Encourage more trackers to set things up. Yeah, okay, that's a good thing, because you can probably imagine that some content, okay, for example, spreading kind acts or spreading need from sort of areas that are under war, okay, and some of those guys need help. Okay, so those information usually, and unless you maintain server, otherwise it's hard to get the information out, get the news out. So maybe one can actually set up a P2p, a news network there, allowing these guys in poor area to upload their footages, okay, so that the rest of the world will know what's going on there. Yeah. How about a P2p news network, okay, so that we could see things that we normally don't see from an area that's much less resourceful. Okay, there's no way to maintain servers from those locations. All right, so poly tracking. Interaction. Right. Okay, bye, Shanting. Okay, I know having exams is a little bit stressful. Okay. I see you tomorrow at 10:20. Okay. The exam, I hope you enjoy it. Okay, instead of being overly nervous about it. Okay. The point is still trying to teach you more, enforce a little bit more. Okay. Boris, bye. Yuhao, bye. Shanting, Jieming, Yuxiang. Okay, all of you. Okay. Justin, I think Justin. Okay. Justin? Oh, Justin, you're probably Youxiang. Yunqi, bye. And we end stream now.